Alright, this is where we left off, but we're actually going to skip the Arrhenius equation. So we're going to pick up with what is known as reaction mechanisms. So this is another place where I feel like we've kind of veiled some things about chemistry until we were ready for them, sort of like we did with equilibrium. We never talked about reactions going backwards until we got to the equilibrium chapter, and now we say all reactions can go in either direction practically. And so now we're going to talk about something called reaction mechanisms. So actually most reactions that occur do not occur in one step. For example, the reaction 2NO plus O2 yields 2NO2 does not occur by two NOs and one O2 bouncing into each other with a lot of energy and spitting out two NO2s. It actually occurs in two what we call elementary steps. And elementary steps are steps that occur in order for a reaction to completely take place. For example, in this reaction, the first step is where those two NOs actually join together to make an N2O2. So those two NOs collide and stick together and form N2O2. That N2O2 then will react with the oxygen to form two NO2s. So it's a two-step reaction. And when we put the two mechanisms together, this N2O2, which is a product in the first step and a reactant in the second, will cancel out and we'll be left with just what is our overall reaction, which is the same thing you see here. So mechanisms are a series of steps, series of elementary steps we call them, but they always sum up to the overall reaction. So when we put our reaction mechanism or our elementary steps together, we'll get the overall reaction. It's just kind of showing the behind the scenes, what is really happening behind the scenes. A little bit of vocabulary about these mechanisms is something called a reaction intermediate. So if you have a substance that's produced, like this N2O2, but then consumed in the next or some subsequent step, if you've got 3 or 4 steps, it is produced and then consumed during the overall reaction, it is called an intermediate. And those always cancel and you never see them in the overall reaction. So without this kind of behind the scenes footage, you would never even know that that was part of the reaction. If we know the mechanism for something, we can actually find the rate law from the mechanism. Remember that a rate law can only be found experimentally. So you've got to do some sort of experiment to find the rate law. However, once you do that, or once someone else has done that and knows the elementary steps or the mechanism, that can give us some clues as to the rate law. For example, this reaction here, NO2 plus CO yields NO plus CO2, is known to have this rate law. It is known to be rate equals K, the reactant NO2 to the second order, and the reactant CO to the 0 order. So they actually don't even include CO in the rate law because anything to the 0 order is 1. So it has no effect on the rate law. Alright, so we said you cannot look at the balanced equation and determine the rate law. Because if you look at the balanced equation here, NO2 has a 1 as its coefficient, yet it's second order, and CO has a 1 as its coefficient, yet it's 0 order. However, if you are looking at elementary steps, you can actually use an elementary step to figure out the rate law. For example here, this reaction occurs in 2 steps. So step 1 is known to be what you see here, and step 2 is known to be what you see here. And the rates for these steps can be predicted. So the rate for step 1 can be predicted to be rate equals K NO2 to the second order because there are 2 NO2s in this step. And the rate for the second one can be predicted to be rate equals K NO3 to the first CO to the first because both of those are involved once in that step. Okay, so we cannot predict a rate law from a balanced equation. However, if we have elementary steps, then the rate laws for those steps are predictable. Now, if we look back at what we saw as the rate law on the previous slide, the rate law was the exact same as this first step. So that tells us something about that step compared to the second, and we'll talk about what that means. So for any elementary step, if you have an elementary step, not a balanced equation, an elementary step, you can use the coefficients as your order. Alright, so far we know that this is the rate for step 1, and this is the rate for step 2. And now they're telling us that step 1 is slow, and step 2 is fast. Right? So in step 1, you are slowly making these products. And as you make the NO3, step 2 is fast. So as soon as you make that NO3, it gets used up in step 3. It is an intermediate, right? So if step 1 is going really slow, and you're using that NO3 as soon as it's made in step 2, this CO, adding it, is not going to change your rate any because it's in the fast step. And it's this step before it that's determining our speed. So the key is that the slow step always determines your rate. The slow step determines your rate. So the rate law is always the rate law of your slow step, and if there's any steps before it, they can contribute to the rate law as well. But in this case, there's no steps before it. All right, so let's say that again. The rate law for the slow step and any steps before it, if there are any, is the rate law for the reaction, because the slow step determines the rate for the reaction. These subsequent steps, even though they have their own rate law, their rate really has nothing to do with the rate of the reaction because the slow step above is what is controlling our rate. So think about an assembly line. If someone early on down the line is going slow, they're going to control the rate for everyone that follows them. So no matter how fast Johnny is at spot 5, if Sarah's going slow at spot 2, he can't speed up the overall reaction. So the rate is determined by our slow step in our reaction. As long as the mechanism has a slow first step, like we see here, then the rate law for the overall reaction is the rate law for the first step. So that's what we saw here. The first step was slow. The rate law for the first step is the rate law for the overall. However, if your second step is slow, you have to think about the first and the second step. Okay? So if your subsequent step is slow, like your first step is not slow, it's fast, then when you look at your slow step, you've got to look back to figure out the overall rate law. Alright, so here we have step 1, and they wrote the rate law for step 1, and then step 2, and they write the rate law for step 2. Now, they make this a little bit more complicated, so I'm going to try to simplify, but I do want to point out something. If you have a fast first step, and then your second step is slow, your first step is going to establish an equilibrium, so that your second step is going to pull that product whenever it gets ready for it, okay? But it's moving pretty slow. So you're going to have a forward and reverse first step. It's like going back and forth, waiting on the second step to be ready to go, okay? It's like, I don't know if y'all have ever experienced this, but whenever I used to get ready for school when I lived at home, I always felt like I was ready before my mom. So I was pacing back and forth, waiting on her to get ready. Kind of the same deal. So if step 1 is fast, it's going back and forth, waiting on step 2, which is slow. So the point, though, is when we consider the rate law, we have to consider that the first step is reversible. So it actually has 2 rates, the forward and reverse. and then you have the rate for the second step, your slow step. So what I say to do is, and they're going to complicate it a little bit in the next part, and I'll try to skim over that. If your second step is slow, or your third, or your fourth, or whatever, look at that step and any that come before it and cancel anything that's an intermediate. So here we have slow and the one that comes before it, and look, NO3 is an intermediate, so it's going to cancel. So it's not going to be in my rate law. And then I'll put these two rate laws together. So I'm going to have NO squared, because there's an NO there and there, and then I'm going to have O2 as my overall rate law. Okay? So if your first step is not your slow step, you're going to need to look and cancel anything that can cancel in the first two steps, or the first three if your slow step is your third step, and then put everything else together to figure out your rate law. So I have two NOs, so NO will be to the second order and O2 to the first. Alright, so that's what you see down here. And I'll show you that one more time. This is the work that they do if you want to pause and kind of see how they're thinking about it. But I've got NO3 here and NO3 here, and my second step is slow, so I'm looking at 2 and 1. NO3 will cancel. That leaves me with two NOs, so NO squared and an O2. Again, I can only do that because these are elementary steps. If I was looking at an overall reaction, I could not write the rate law in this way. And also, if the slow step is your first step, then your rate law is just based on your first step. But since it's the second step, I have to look at the second and the first. If there was a third step and the second one was slow, I would ignore the third one in the rate law because it would have no effect on it. Alright, so how do we determine a rate law? Experiment, experiment, experiment. Then they use the rate law to figure out what the elementary steps are. Because the rate law is going to tell chemists what the slow step is. And then they try to figure out what the fast steps are. They can use some experimental detection devices to spot intermediates. And then they build up evidence to support a proposed mechanism. Now, a mechanism is a hypothesis and it can build to a theory, but it is always refutable. So someone else could come up with more evidence that says, oh, no, I found a different intermediate, or actually, I found a different step that works better, so let's look if this makes more sense. They'll go collect more evidence. So it's not like someone got on the magic school bus and watched the reaction and they know how it happens. Okay? It's just evidence that's built over time to propose the mechanism. Here's some examples of some elementary steps and the rate laws that would go with them. Again, these are elementary steps, not overall reactions. So if you have a unimolecular, that's a single molecule like A, in your elementary step, then your rate law is just rate equals K, A to the first. If you have a bimolecular where they're both the same molecule colliding, rate equals K, that molecule squared. If you have bimolecular with two different molecules, rate equals K, the concentration of both those molecules. So notice unimolecular is first order. Bimolecular, you've got two molecules involved, it's second order. If you have termolecular elementary steps, like 3 A's, A to the third, 2 A's and a B, A, B, C, etc., those are all third order. But hold up. Remember we said that the only possible orders were 0, 1, and 2? So how did this get to be third order? Okay, this is the point that they're making down here. Termolecular elementary reactions are very, very rare because that would require that not 1, not 2, but 3 particles collide in the right orientation with enough energy at the same time. That is very, very rare. Right? So these termolecular reactions, if they do happen, they are going to be slow. You need to be able to explain why a termolecular elementary step is not probable. Okay, so make a note. You've got to be able to explain why a termolecular elementary step, or why an order of 3 is not probable, because that would require 3 things to collide with the right orientation and the right energy at the same time. Not going to happen very often. All right, another note that they put down here is this rate constant, which we see in every single rate law. It is going to go up when the temperature goes up. All right, so here we see 2 different elementary steps. Process 1 has an elementary step that is bimolecular. Process 2 has an elementary step that is bimolecular. And it tells us that these are the slow steps for these 2 processes. So these processes have other steps, but they're just showing us the slow ones in these 2 different processes. And then they give us the rate constant for each of them. So which process would go faster, process 1 or process 2? Well, process 1 has a higher rate constant, right? 10 to the negative 4th is higher than 10 to the negative 6th. So my guess is process 1 would go faster because it has a higher rate constant. Now it's important that we note that we can only compare these 2 because they do have equal molecularity. They're both bimolecular. All right, here we have the rate law for 2 elementary steps, and they want to know which one is likely to proceed at a higher rate. So process 1, that is termolecular, or 3rd order overall, and this one is bimolecular, or second order overall. Here's an example of where they kind of pull out that termolecular concept. So which one's going to be faster? Well, the bimolecular process is much more likely to occur because it only requires the collision of 2 particles, whereas process 1 requires 2 A's and a B to collide with sufficient energy and in the correct orientation. Again, not going to happen very often. All right, we'll pick up with catalyst on the next video, which should be pretty short. Actually, sorry, don't go anywhere. I'm back. This section is very simple. I just flipped through it and kind of refreshed my memory about what's included here. I just want you to read over this and be able to answer the questions in the homework and then ask me if you have any questions. So I won't do a separate video on catalysis.